In this class, we're going to consider separable differential equations. So there are many different types of differential equation, each has its own format, and it's really that format that dictates the method of solution. So the challenge for you as a student is to learn the different formats, the different types, so that you can recognize what kind of differential equation you're working with and then apply the appropriate solution. So we're going to focus in this class on these separable differential equations. These are not the most difficult type, but they're a great starting point. They give you insight into how all differential equations approximately are solved. So we'll work these two examples in a moment. Before we get there, let's take a quick look at the theory. So the first thing for all differential equation types is to learn the format. What am I looking for? What does this type look like? And the format we're looking for with a separable differential equation is basically to have our derivative, so first derivative, so dy dx, on the left-hand side. Remember, y and x may not be the letters in your question. I'm just going to go with the standard y and x. It could be some other letters, but the important thing is it's a first derivative here. And this is going to be equal to the product of a function of one of the variables, so f of x, multiplied to a function of the other variable, so g of y in this case, okay? So that's basically the format for a separable differential equation. So you can see already that this first example is exactly in that format. We've got the first derivative here on the left-hand side. We've got a function of x multiplied to a function of y, so that's fine. This one's in a slightly different format. We do not have the first derivative isolated, so we're going to have to work a little bit harder. And actually, we're going to have to check and see, is this even a separable differential equation? If it's not, then we can't use the method that we're going to look at in this class. So getting back to our theory, at this point, we know what the format looks like. Why is it separable? Well, it's separable because we're going to separate out the variables. In other words, we're going to put the x terms on one side of the equation and the y terms on the other. So we're just treating our dy dx, the first derivative notation, as a fraction, so we can move terms around as a fraction. If we take the g of y term to the left, that's going to become 1 over g of y. So just dividing both sides basically by g of y. So 1 over g of y, and then we've got our dy there. And then we're going to multiply both sides by dx to get f of x dx on the right-hand side. So at this point, we've completed the separation. We've got the x's on one side and the y's on the other. And then we're just basically going to integrate both sides. So this is an equation. You can do the same thing to both sides. In this case, the operation that we're performing on both sides is integration. And you're going to see a lot of integration in these, well, always in these types and in differential equations in general. So this then, with an actual problem, would allow us to get our final solution. And what is that final solution? Well, it's going to be some function of the variable. So in this case, we'd be looking for y to be some function, let's call that h of x. And that's what your final solution is going to be like. So remember that the solution for a differential equation is not some numerical value, as in the case of maybe a linear equation. It's going to come out to be a function. So we're looking for functions as our solution. So this is roughly the method that we're going to employ to solve these two problems. Okay, so let's move on and take a look at these examples. So this one we already kind of checked to make sure it's in the correct format. So that one's fine. That's got to be your starting point. Make sure you know for sure that you're dealing with the correct format. If you're not dealing with the correct type of differential equation, then the method that you apply is not going to work out. So this one is in the correct format to be separable. So we can go ahead and separate and then apply our solution method. So just doing exactly what I did over here. Let's basically get the x's on one side and the y's on the other. So we're going to end up by dividing both sides by y squared to get 1 over y squared on the left-hand side, dy, equals x dx on the right-hand side. So at that point, we've got our separation completed and we can just go ahead and integrate. So nothing else to do here. So the integral of 1 over y squared dy equals the integral of x dx. Because we're going to be using integration to solve these problems, you're going to want to think about your integration rules. You're going to want to check that things are in integratable forms. This guy's in an integratable form to use the power rule. This one is not. So if you've not done integration for a while and you're working differential equations, you might just want to review integration techniques. So this is not in the correct format, but I'm going to make it into the correct format just by bringing the y squared term to the top using one of the indices or exponent rules. That becomes y to the minus 2 dy equals the integral of x dx. So I could have integrated this term at this point, but I'd rather just keep both integrals just so that I can, on the same line of working, integrate all the way through the equation. But that's kind of personal preference. You could integrate from this point if you wished. So these are both now in the correct format to integrate. So using the power rule, this would become minus y to the minus 1, and that's going to equal 1/2 x squared, or x squared over 2 if you prefer to write it like that. And I'm going to put my constant of integration on this side. So a common question is what to do with the plus c. These are both indefinite integrals, so we need a constant. You could put a constant, I guess, over here. This is an indefinite integral, but we could merge the constants anyway. So the way we go about these, we just apply the constant on the side of the equation that's got the variable in the function. So you'll see by experience that that's never really an issue. So just learn to apply it on the correct side. At this point, we've almost solved, but we don't quite have our y term isolated. We've got it isolated in one sense, but it's got this negative in front, and it's got a negative 1 power. That's not necessarily wrong, because we would call this an implicit solution rather than an explicit solution. This is an explicit solution. In other words, it's y equals. This is not quite there. Let's leave it as an implicit solution, but let's maybe get rid of this minus 1 power. The minus in front's okay. We can get rid of the minus 1 power. We don't like to leave negative powers by just putting it back to the bottom of the fraction. So it's going to be minus 1 over y equals everything else on the right-hand side. Okay, so that would be the general solution, and it's written in implicit form. And we could manipulate it into explicit form, but we're just going to leave it like that in this particular case. So sometimes with differential equations, you'll write the answer in an explicit form, sometimes in an implicit form. Sometimes the question will dictate how to write it. Sometimes it'll ask for it to be written in a particular form. So just by experience, you'll know what to do in those different scenarios. So that's pretty much an entry-level, straight-up use of the method of separation of variables to solve that differential equation. Let's take a look at this guy. So we noted already that this is not in the correct format. And if you think about the format that we're looking for, it's not so much a focus on this product. Well, it kind of is, but it's a bigger focus, I think, on this isolated first derivative. So here we do not have the first derivative on its own, but we could manipulate the equation to get it on its own just by dividing both sides by x squared. So let's go ahead and do that. If you get the dy dx, or your first derivative, whatever the letters are, on its own, and the equation is still not separable, in other words, if you cannot then at that point separate out the variables, then it's not a separable differential equation. So probably your best check here is not to focus on getting the product of functions. It should be a product of functions, but focus on getting this term on its own, then see if you can make this into a product of functions. If you cannot, then it's not separable. You need to use some other method. So this is not quite in the right format, but by a bit of experience and manipulation, you'll know what to do. So here on the top line, there's a common factor of y. So just making that y bracket 1 plus x like that. All of this over x squared. Checking in with our format, is that a product of the functions of x and y? Not quite, but we can manipulate it further just by taking this y term and putting it on the end. Remember, the order in which you multiply does not matter. So we could just make this actually 1 plus x over x squared. We could actually just put the y over here. So now we've made this into explicitly some function of x multiplied to some function of y. So that then matches up with the format we're looking for. So a little bit more work already in this problem just to even validate and verify that it is a separable differential equation. So now we know it is, so we're good to proceed. So you might need to do that in some problems. It just depends. Sometimes they're straight up in the correct format, sometimes they need a bit more work. So we're going to go ahead and separate the variable. So I'm going to do that just as I did over here. I'm going to bring the y term to this side. That's going to give me 1 over y dy, and then I'm going to leave the x terms on this side. So 1 plus x, I can drop that bracket now over x squared dx. So at this point we've separated, so we're good to go ahead with our integration. So let's have a think about, are these in integratable forms? This guy is using a natural logarithm. If you recall, hopefully you recall, if not review, how to integrate 1 over x or y, because you're going to see that quite a lot in these. This integrates as the natural log of y, so that one is actually in an integratable form. This one's not in an integratable form, but we can manipulate it a little just by splitting it into two fractions. So we're going to get 1 over x squared plus x over x squared. Okay, and all of that dx. So again, by experience, you'll know what to look for here, but really this is just back to integration. This is back to sort of calculus 2 probably. So we've now got 1 over y dy on the left-hand side, so that term is good to go. These are still not integratable. This can be integrated using the power rule if we bring the x squared to the top. So let's do that and make it an x to the minus 2. That's kind of just like what I did over here. We can divide this fraction top and bottom by x. If we do that, then we're going to get 1 over x as an equivalent fraction, all of that dx. And then this term is now integratable using the natural log, just in the same way that this guy is. So again, a little bit more work in this problem to even get it from the separable form into an integratable form. Remember, that's always going to be your goal. Now we can go ahead and integrate. So just taking a line to put in your integral sign. So the integral of 1 over y dy equals the integral of all of this stuff on the right hand side. Okay, so let's just go ahead and integrate. So like I said, this guy here integrates to the natural log of y. This guy, using the power rule, is going to be minus x to the minus 1, just the same scenario I had over here. And then this guy, 1 over x, also integrates to the natural log, so the natural log of x in this case, and we'll put our plus c on the end. So at this stage, we now have an implicit solution to this differential equation. That's a little bit like the stage we were at here. We could stop at that point if that was good enough, or if the question dictated putting this in an explicit form, then we're going to need to go further. Let's maybe go a little further in this case. I'm just going to kind of stop at this point, I guess, and say, right, we are kind of done in a sense here, but we could take it further. So what else can we do? Well, one thing we could do just to tidy up is make this term a little nicer. So we can make that the natural log of y equals minus 1 over x. I'm just going to leave everything else the same. And there's a little trick that we can employ here. Because you're going to see a lot of natural logs in these questions, one thing you can do with your c, remember that the constant is an arbitrary constant, so you can kind of make it whatever you want. We're going to make it into the natural log of some other variable, let's call it k. And the reason why we're going to want to do that is just to combine the terms. So if I go ahead and do that, so just basically changing that term, and this is just purely for algebraic sort of convenience. We've now got the sum of two logs here, and you'll remember hopefully from your log rules from the distant past maybe, that you can merge these into the log of the product of the x and the k. So that's going to become minus 1 over x plus a single log of x multiplied to k. I'm going to spin that around and make it kx because x is our variable here. And that's just going to make things a little more convenient. So here we've still got the natural log of y. Now why is that more convenient? It's more convenient because we're now going to take these two sides of our equation and use them as a power on an e as in the exponential number. We're allowed to do that because if the two sides of the equation are indeed equal, then it must still be the case that using them as a power in this e still allows us to make an equation, okay? So that should be fairly intuitive. The reason why that's now useful, we can now basically cancel off the e and the ln. So remember, ln is just the natural log to base e. These cancel. And the left-hand side, that's just going to leave us y. That's what we were looking for, to explicitly get an answer in terms of y. And then over here, we've got a base number and we've got a sum here in our power. That then can be broken down into, or changed at least, into e to the minus 1 over x multiplied to e to the natural log of kx. But we know again that these are going to cancel just like these cancelled here. So this kx is going to end up multiplying to this term. I'm going to bring that in front. So in other words, it's going to end up as kx, maybe just use a bracket here to keep it neat, e to the minus 1 over x. We've got y on its own, so we've got this in explicit form. We could, I suppose, make this a little neater by getting rid of the negative power. We could achieve that just by turning this into a fraction. So we're going to have kx on the numerator, and then we're going to have e to the 1 over x, positive 1 over x on the denominator. So a little bit more work involved there. we went from having the solution here in an implicit form, so we could kind of say in one sense we were done here, but we've worked some algebra just to put it here in its final explicit form, because that might be required in the question. It really just depends what the demands of the question are. So you can see by working these two examples, this kind of entry-level question was quite short. We solved it quite quickly. This one had a lot more work. We had to first of all make sure the equation was even separable. Once we had completed that check, we then had more work to make it, well, separated and in an integratable form. And then to get it in this explicit final solution form, we had to do a little bit of algebraic manipulation. So you'll learn how to do that by experience. Every different question will require something slightly different. This required a little bit of log work and exponent work to get it into this final form. So these separable differential equations are really important. They're one of the first types you want to learn. They're a fundamental type of differential equation, so it's definitely worth spending a bit of time getting familiar with these, not only as a skill in themselves, but just to give you insight into how all differential equations are solved. So spend a bit of time working some practice problems on this type, and then when you're ready, move on to the next type of differential equation.